session is going to be actually purely combinatorics. So purely about questions from combinatorics. And in particular, this question, which was called the Kneser conjecture. And so I need to introduce to you some notion. And the first one, which is very standard in combinatorics, is what we call a hypergraph. So take X is a finite set, okay? And a finite set system or a hypergraph on the set X is just a family of subsets of X, okay? So a subfamily of the power set. So finite set system, that's kind of the old-fashioned word. Today they call it hypergraph, okay? So, I mean, it could be anything. So X could be, let's say, 1, 2, 3, 4. And your hypergraph, which we would define or sometimes write, so F, X, E, no, H, X, F, like this. F could be, for example, 1, 2, 1, 3, 4, 2, 3, 4. Okay? So, well, maybe I should put brackets like this. Usually we call these the edges of the hypergraph. Okay? You can, if you want, you can think of it geometrically. It's not necessarily useful. But you call the elements, you call them the vertices, right? And so what are the edges? Well, we have an edge 1, 2. We have an edge 1, 3, 4. And we have an edge 2, 3, 4, like this, right? And this is a hypergraph or a set system. And this is one of the basic objects. In finite combinatorics, basically everything can be formulated in terms of a question about a hypergraph, basically. Okay? And one notion is we say that the hypergraph is intersecting if every pair of edges intersect. Okay? So this is intersecting. This set and this set contain 1 in common. This set and this set contain 2 in common. This set and this set contain 3 and 4 in common. Right? So that's an intersecting hypergraph. And there are tons and tons of theorems. There are whole books about various properties of hypergraphs. Okay? And notice that if every edge has size 2, then this is what we usually call a graph, right? And this is just a more general version of a graph, where the edges don't have to have exactly 2 vertices, they can have more. Okay? In fact, we defined earlier a simplicial complex or abstract simplicial complex. That's also a type of hypergraph, but it has an additional property that it's closed downwards by inclusion, right? Remember, when we defined abstract simplicial complex, it was just a family of sets or family of subsets of this set X, but it had the additional property that if some set was there, then every subset was also in the family. But for hypergraph, we don't require that. So this is kind of the most general version. Okay, and then we have the notion of intersecting hypergraph. Now here is a question from 1955, which says let n and k, n greater or equal to k, greater or equal to 1. These are integers. And consider this hypergraph. Now, what does that mean? So when I write like this, it usually means the set 1, 2, up to n. Okay? And this notation here, set n, or integers 1 to n, choose k, that just means the family of all k element subsets. Okay? So this is the family of all k element subsets of n. Okay? And the question asked by Kneser in 1955 is, given fix n and k, what is the smallest number m so that you can partition the family F, so you can partition all these k element subsets into families f1, f2 up to fm, such that each of these is an intersecting family. Okay? And so this was asked in 1955, and it's a very natural question. Already in combinatorics, people had studied things about intersecting hypergraphs. And so this was a very simple and natural question. Take that family. It consists of n choose k elements, or sets, right? And now you want to split that entire family into intersecting subfamilies. How few families do you need is possible to do this, right? And so this was asked by Kneser in 1955, and they solved a few cases like some values of n and k. And then it was only 20 years later, more than 20 years later, that Lovas, famous Hungarian mathematician, he solved this conjecture. And his solution, this is really the starting point of the topic that we've been talking about here, which is called topological combinatorics, because he showed that the solution of this is actually by the Borsuk-Ulam theorem. Okay? And that's what we're going to see today. That's our main topic today. And this is considered still one of the most sort of amazing applications of the Borsuk-Ulam theorem, because that question doesn't look like it requires or asks for topology at all. Right? OK, so the problem statement is clear? Yeah. OK, so we're going to reformulate this in terms of graph theory. And that also allows us to take a more general viewpoint, in fact. So take a set system so I use set system, sometimes I say hypergraph. It means the same thing. So take a hypergraph f, and you define what's called the Kneser graph of f. Okay? And sometimes they call this the disjointness graph. Now, what are the vertices of this graph? Well, the vertices are the sets, or the members of the family. Okay? So each vertex is one of the sets of the family. So just imagine you have your family f equals, let's say, set 1, set 2, up to set m, right? Now I'm going to create a graph. It's going to have vertices. And each vertex just gets labeled by its corresponding set. Like this. Okay? Now, when do you make an edge? Well, you make an edge if and only if the two sets are disjoint. Okay? So this edge is here. This is if and only if S1 intersect S3 is empty. Okay? And so this is called the Kneser graph of the family F. And yeah, there's some notation here. KG. So that just means Kneser graph of F. Like this. Okay? Now, suppose F is an intersecting family. So F intersecting what does it mean about the Kneser graph of F? How many edges does the Kneser graph have if your family is intersecting?
No, 0.
0 edges. So then this just consists of vertices, no edges. Sometimes we call that an independent set. Okay? Call that an independent set of edges. Now, let's go back to the case when F is n choose k. So the Kneser conjecture, right? F is this family. And now I'm going to look at the Kneser graph of F. Now, the Kneser conjecture was I want to split this into subfamilies, F1 up to Fm, such that each subfamily is intersecting, right? So I'm going to write this as a union F1 up to Fm. What are you doing in the graph? Well, you're splitting the vertices. You're taking the vertex set. You're splitting into a set of vertices here, set of vertices here. So let's call this V1, V2, V3, up to Vm. And each of these is an is an independent set, right? Which means there are no edges here. Which means the edges only go from different groups, no edges inside. But what is that? That is precisely what in graph theory we call a coloring. So you can color all of these vertices green, color all of these vertices blue, all of these vertices orange, right? And no edge has the same color at both ends. So that's what we call a graph coloring. And Knezer's conjecture is asking, find the smallest m so that you can split this into m intersecting families. That's equivalent to saying, find the smallest number of colors so that you can color the vertices so that no edge has the same color at both ends. And that is precisely what we call the chromatic number of the graph. So Knezer's conjecture is simply asking, what is the chromatic number of that graph? Okay, so, and let me just point to it here. When f is this family of all k tuples of n, we denote that Kneser graph simply by kg n, k. All right? And so that's how you reformulate the Kneser conjecture into a graph theory question and a graph coloring questions. All right? Is it clear? Okay. So maybe first I'll show you some examples of Kneser graphs. Well, let's solve some simple cases of this graph coloring question. So this kg n, k, this is by definition the Kneser graph of the set system n choose k, like this. Okay. Now let's do some cases. N is less than 2k, right? What does the graph look like? How many edges does this graph have?
0.
Zero edges, right? Yeah. Because I'm taking k element subsets from an n element set. If n is less than 2k, there cannot be any disjoint pair. This is disjoint. This is a, so here, just independent set. So chromatic number of k, kg, and k, in this case equals, what is the chromatic number of this set, this graph here? 1. Yeah. What about n equals 2k? What does the graph look like now? Yeah? I think you have the right idea. It is a bipartite graph, but it's what we call a matching. Okay? So in this case, say n was 6 and k was 3. So for example, take the vertex with label 1, 3, 5. It has a unique neighbor. And it's precisely the complement of this, right? 2, 4, 6. 1, 3, 6 has a unique neighbor, 2, 4, 5, etc. So this is just a matching. We call this a matching. Chromatic number is 2. As soon as there's an edge, you need at least 2 colors. Right? Okay, let's see. I think I have pictures of those examples here. Oh, I forgot that one. KGN, N1. Well, we see that's the complete graph, right? Every vertex just gets a single integer. 2 distinct integers are, of course, disjoint sets. So that's a complete graph, and the chromatic number is n. Okay. Do we see the pattern, what the chromatic number should be in general? So here is another example. That's this first one here, right? That's just independent set. Here's a matching. The first interesting case, so all of these are non-interesting, and it's easy to see what the graph is. It's easy to see what the chromatic number is. First non-trivial case is this guy. So that's when n is 5 and k is 2. Then you get the famous Peterson graph. Okay? And n equals 5, k equals 2. Right, so it becomes more interesting when n is greater than 2k. Right? Then you really get some kind of graph, but you also don't want k equal 1, because then it's just a complete graph. So this is the first non-trivial case. And this is just one way of labeling that graph. But if you sit down and try to do it by hand, it's easy. So 5 choose 2 is 10. It has 10 vertices, right? If I look at a vertex labeled AB, I know that it has exactly 3 neighbors, right? Because what are its neighbors? Well, you look at the set 5 minus AB. That's a set of 3 elements. And you take all the possible pairs of those 3 elements, there are 3 of them. So every guy, it's regular of degree 3, right? And then it turns out that the structure is a little twisted and gives you this Peterson graph. Okay? And have you seen this graph before?
Yes.
I mean, if you studied some graph theory, you will encounter this graph because it's very famous. It appears as kind of a counterexample to many things, and it's a kind of a graph that appears many places in mathematics. Strangely, another place it appears is the projective plane.
Projective plane.
Yeah. So remember, we did a triangulation of the projective plane earlier. First class, we did a triangulation of the projective plane that looked like this, but you labeled here A, B. So in first lecture, A, B, C, and then maybe these guys D, E, F. Okay? So that was our triangulation of the projective plane. That was a triangulation of the projective plane. If you remember this, right? It's a circle with the opposite points identified. Now, here's what you can try to do, and I'll leave this to you as an exercise. You look at what's called the dual graph. Put a vertex inside every face and make an edge when the 2 triangles share an edge. So for example, this guy, BC, same edges here, so there should be an edge that goes across and comes here. Okay? And so on. Now keep doing this. That is the graph you get. So that you can check for yourselves. Okay? So this is somehow a graph that appears many, many places. What is the chromatic number of this one? So chromatic number can you color it with 2 colors? Why not? There's an odd cycle, right? The outer thing is a 5 cycle. 5 cycles cannot be colored by 2 colors. Odd cycles cannot be colored by 2 colors. In fact, as soon as your graph is not bipartite, it's equivalent saying there's an odd cycle. Okay, so we cannot do it by 2 colors. What about 3 colors?
Maybe we can.
Yeah, but don't. Yeah. You're looking ahead. Yeah, well, that's cheating. Okay, but so what he is suggesting is the following coloring. So define vertex at V1 is those S such that 1 is in S. Okay? So it means let's color those with blue. I'm not going to draw on this thing here, but this gets blue, this gets blue, this gets blue, and that one gets blue. Clearly, those blue vertices have no edges between them. They all contain the vertex 1. V2. Any guess what that should be? If I follow this pattern here. Any one that contains 2. And let's say in F minus V1. Okay, so I remove the guys that I already colored blue. I look at the remaining things, and if you contain 2, then use that color. So this one, and this one. Right? Clearly, they don't have a common color. Now, how do I color the rest?
We have only one set, 3, 4, 5.
Yes, so the remaining ones, the remaining vertices, so after I colored V1 and V2, anything that has 1 or 2 has been colored. Any set that has 1 and 2. So the remaining sets have only elements 3, 4, 5. And no matter which pair I take from 3, 4, 5, they intersect. So I can use the same color for all of them. So that is a 3 coloring of this graph. Right? So in fact, the chromatic number is 3. We showed there is a 3 coloring, and since there's a 5 cycle, there is no 2 coloring. Right? It's written there, 3. Okay. So that is the A3 coloring. I think there are other 3 colorings, but this is one of them. Now, we generalize this to a general coloring of the Kneser graph. And so it's just following that same example. Okay, so this is the same coloring, just generalized. So V1 is all the sets that contain element 1. Now you remove all the guys that got colored 1 in the first round. And now you look at the remaining sets. None of them contain 1. And those that contain color 2, you color those, right, with color 2. And you keep going all the way up to n minus 2k plus 1. Okay, so you remove what you colored before, you look at what's left over, and you look at the element that contains Vi, or the element I, and you color that with color I. You do this all the way up to n minus 2k plus 1. Then, how many vertices or how many elements are left in your set? Well, there's exactly 2k minus 1 elements left. Okay, so you removed 1, you removed 2, you removed 3, all the way up to 2k plus n minus 2k plus 1. So now the remaining sets, they are subsets of a set of size 2k minus 1. And since you're taking k tuples, they pairwise intersect. So you have 1 leftover color there. Right? So this shows that the chromatic number, so for n greater or equal to 2k minus 1, the chromatic number of the Kneser graph nk is at most n minus 2k plus 2. And in fact, what Kneser's conjecture is saying is what he originally said. It's not the question that I wrote there, but the original Kneser, who originally came up with this problem, he of course noticed that he could color it like this. Right? He noticed this coloring, and his question was, is this actually the right chromatic number? Or could it possibly be less? And that was the open question. So the Kneser conjecture is that for n greater or equal to 2k minus 1, the chromatic number of kg and k equals n minus 2k plus 2. And you see this coloring that we gave here, it's kind of trivial in some sense, right? Because each of these sets, these first sets, each one of them is trivially an intersecting family, because each of them contains one fixed element, right? And the last set is trivially intersecting because you're taking k element subsets from a 2k minus 1 element set. And those are two of the basic trivial intersecting families. And there are many theorems about the intersecting families, and many of them show that actually these trivial intersecting families are kind of the largest ones in some sense. And many theorems in combinatorics are theorems of the type saying that you want to show that there is some structure, or a certain structure. You ask, how good is a certain structure? And then you show that, well, here's a trivial structure that satisfies my property. And then you want to show that, well, in fact, that trivial structure is the best one. And this is exactly that type of theorem. This is kind of a trivial coloring, and you want to show that. And you don't really have to think to make this coloring. That's what it means that it's trivial. It's once you have one idea, then you see, OK, this is trivial to make this coloring, right? And the question is, well, is it possible that if you think harder, you could make a better coloring? And the answer, which often happens in combinatorics, is, or in this style of combinatorics, is, well, in fact, it doesn't matter how hard you think, you will never be able to do better than this trivial coloring. Okay? But what's difficult to show is that you cannot do better. Right? All right, so I think we can move on to the proof of the Kneser conjecture. And this is the theorem proved by Lovász, which says that indeed that is the chromatic number. Okay? And Lovász's original proof was quite different than the one I'll show you here. This is a more modern proof. But Lovász's proof was more general because you could, he'd built a more general theory to prove this theorem. But then later people extracted from it very nice and simple proofs. But Lovász did use the Bourse-Coulomb theorem though. And that is somehow unavoidable.
So
yeah?
K is bigger than 2k minus 1. Yes.
It should be n greater than 2k minus 1. Yeah. That's a typo. So you need n bigger than 2k minus 1, because if n is 2k minus 2 or 2k minus 3, all these cases we saw, the chromatic number is just 1, right? So that formula doesn't hold anymore. So it's 1, and then this formula kicks in as soon as n becomes greater than 2k minus 1. Yeah, so thank you for pointing that out. This is a typo. Shouldn't be a k there. OK, so how do we prove this? Now we have all the tools. But like I said, this is not originally how the proof was discovered, but this is one of the nicest proofs. So we need to show that my graph is not, you cannot color it by one less color than this. Okay? That's my goal. So for contradiction, assume, so suppose we're given a 2n minus 2k plus 1 coloring of, okay, n and k, n greater than 2k minus 1 fixed. So for some large n and large k, suppose this theorem was false, right? And if it's false, it means there is some coloring using this many colors. Okay? So just fix that coloring now. And then I'm going to set d equals that number here. So set d equals n minus 2k plus 1. And now choose a set of vectors x, so unit vectors, so those are points on the sphere, but let's think of them as unit vectors. Choose a set x of size n And this set should be what we call in general position or general linear position. Now what does it mean? It just means that any d of these vectors are linearly independent. Okay? Now you can choose them freely any way you want. Doesn't matter. As long as you satisfy this general position. Okay? So what does it mean? It means that any d of these vectors form a basis for RD. So, sorry, any... Let me think. Is there a mistake here? Should be any d plus one of them are linearly independent, I think. Because SD lives in RD plus one. Okay? Now, the set you choose, the set of vectors you choose, has size n. So I'm going to identify, make some bijection between the elements in X and the elements 1 to n. Okay? So, in other words, I just take my set of vectors and I just label them 1, 2, 3, 4, 5, up to n. You choose how you want to do it. Okay? And we are supposing that we have our fixed coloring here. All right? Everything clear so far? Yeah. Now what does it mean that I have a coloring of that graph? It means that every k element subset has some color in this set here. Right? And now I'm going to define some covering of the sphere. So take your sphere and take a point x on the sphere, right? Now this point x defines an open hemisphere. Okay, so that is precisely this hemisphere, which are all the guys that make a positive dot product with x. Okay, so it's all this, so that's this open hemisphere here. Right? And I will say that the point x belongs to some set AI if and only if that open hemisphere contains a k-tuple from x with color I. Okay? So how many sets am I getting in this way? How many sets AI am I getting?
Maybe d plus 1.
Really? How many colors did I color my k-tuples?
D.
D, this number here. So how many sets am I getting?
D sets.
D sets, right? So I assume I've used every color. And any d vectors, sorry, any k vectors, which is less than d, will be contained in some open hemisphere. Yeah. So it means that this way I define d sets. Agreed? And it turns out that each of these sets are open. Can you see why? Well, just think of the two-dimensional case. So I have two vectors here, say like this. Here is a set of k vectors. Okay? And I'm looking at the set of all half spaces, or all, I look at the normal vector. Here's x, this is hx. And I'm looking at all x's that contain this specific k-tuple. Right? If I go exactly on this vector like this, do I contain that k-tuple? No, I'm looking at the open hemisphere. This is important, right? This is the open hemisphere containing that k-tuple. So it means the set of x's of half spaces like this that contain that specific k-tuple, that's an open set. And if you look at all the k-tuples of a fixed color, well, it's just a union of open sets. That's an open set. Okay? So this is each AI is an open set. And I have D, so I have A1 up to AD in SD. and these are open sets. This is what I've defined now. And that comes from my coloring. Given my initial coloring of the graph, I can define these sets now. Do these sets cover the sphere?
No.
No.
Well, not necessarily, right? Of course, I chose these vectors arbitrarily. Here's my sphere. What if I chose all the vectors to live like this? It's not a problem, right? Then, of course, this vector here, x, doesn't contain any k-tuple, right? But let's just define AD plus 1 equals SD minus A1 union AD. Okay, that's my last set. This is a closed set. So what do I have now?
Each test is open or closed, and we can use RS mix.
Yes. So remember, we had this version of Borsuk-Ulam theorem, which was covering the sphere by D open sets, or covering the sphere by D plus 1 closed sets, or covering the sphere by D plus 1 sets, each one being open or closed. That's precisely what we have here, right? And that's where the Borsuk-Ulam theorem comes in. What does the Borsuk-Ulam theorem now say? It says that one of these sets contains antipodal points. Okay, so what if A is less than or equal to D? And suppose here's x, here's minus x, and suppose x union x minus x is in AI. Suppose that was the case. Is this possible? Well, what does it mean? Here's the center. It means that this open half space contains a k-tuple color I, right? And it also means that this half space, open half space, contains a k-tuple of color I. Why is that not possible? This cannot happen. Why is that? No?
Because x and h minus x will contain disjoint, and will contain disjoint.
So these vectors have none of these vectors in common.
Yes.
This is an open half space. This is a disjoint open half space. These k vectors are disjoint from these k vectors. But if you go back to the graph, what does it mean? Those two, what is a k-tuple of vectors here? It's a vertex in the graph.
Yes.
This is another vertex in the graph.
Yes.
They should be connected by an edge.
Yes. And same color.
So they can't have the same color. So that situation never happens because we assumed this was a coloring of the Kneser graph. So Borsuk-Ulam theorem tells us that one of these sets contains antipodal points. It cannot be any of these sets. So it's this set. Okay, so again, we have x, we have minus x. And this is in AD plus 1. This is in AD plus 1. So what does that mean? Well, it means that the number of vectors that are here in this open half space
Most k minus 1.
is less than k. Do you agree?
Yes.
If there were more than, or if there were k vectors here, then they have some color. So this belongs to some set. But remember, AD plus 1 is the complement of all of these guys. Similarly, down here, less than k vectors. Okay? So how many vectors are left over? Well,
at least n minus 2 times k minus 1. 2.
yes, which is like this, right?
Yes.
Yeah. And they all live in this hyperplane here.
Yes.
But that's a contradiction of the general position. Then I put too many vectors in a single hyperplane. Okay? So that comes from the choice of general position. So it means that all the remaining vectors live here, but since they're less than k here and less than k here, there are too many vectors that you squeezed into a single hyperplane. And that's the contradiction. And so this proves the Kneser conjecture. So this remaining part is just this same same argument. So here, this should say any d plus 1 are linearly independent. That's a mistake in the notes. But what did I find here? I found that there must be more than d, so at least d plus 1 vectors that live in a hyperplane. Then they are not linearly independent. Okay? So that is proof of the Kneser conjecture. And as you can see, this really, I think this is really ingenious proof. When you first encounter that graph theory problem of the Kneser conjecture, I think it would take a long time to figure out I should use topology here, right? And that's what Lovász discovered, and it essentially started a whole field, because now there's a whole field of solving combinatorial problems using topology, right? But this was maybe the very first example. Let's see. Okay, so I don't think we're going to finish all the slides. So the last section of these slides today are going to be, you can look at yourselves. We're going to do one more question, which is a generalization. So Kneser's conjecture became so famous and this theorem became so famous, many people made generalizations of this. And the one that we'll look at is called Dolnikov's theorem. And so this is quite nice and a little more general. And it introduces the notion of the chromatic number of a hypergraph. Okay, so remember, a hypergraph was just a set system of subsets of some finite set. Okay? And the chromatic number of a hypergraph, this is the smallest number m, so that you have a coloring of the vertices, so that's just a function from the vertices to the set m, with the property that the number of colors that you see for every edge is strictly more than 1. Okay? So this is what we call the chromatic number of the hypergraph. There are many versions of chromatic number of hypergraphs. This is the most basic one, I think. It says that, so I have my hypergraph. Like this maybe, right? Now I want to color the vertices in such a way, so what is not allowed, I'm not allowed to have a single edge, what we call a monochromatic edge. I don't want to have an edge where all the vertices have the same color. Okay? That is one version of what we call the chromatic number of a hypergraph. Some people, they have a different notion. You want to color the vertices so that every edge has all different colors there. I mean, that could be another way of defining the chromatic number of a hypergraph. But we'll just do the one where there is no edge that has monochromatic vertices. Okay? Now, what if you were dealing with just the case of a graph? Okay, so every edge has 2 vertices. And we use this notion of chromatic number. Well, it just says that every edge, which consists of 2 elements, has 2 different colors. So that's just a standard version of graph coloring. So this is a generalization of the standard notion of graph coloring. Okay? And another notion that we need to define is, if you take a subset of the vertices, we can talk about the induced hypergraph. Okay? And so that is just, so you fix some subset of vertices, and now you look at those edges that are contained in that subset. Okay? So in my example here, suppose I took this subset that I color yellow here. What is the induced hypergraph? Well, it's this edge, this edge, this edge, not this edge, right? Because it contains a vertex that I didn't select. And not this edge because it has vertices edges. So you only keep the edges where you selected all vertices. This is called the induced subhypergraph. And here comes a strange parameter. And it was Dolnikov who introduced this. And it's called the two-colorability defect of F. Okay? So it is the smallest number, or smallest number, so that if you delete that many vertices from your graph. So wait, another way of thinking of the induced subhypergraph is you simply delete those vertices, but you also delete every edge that contained any of those vertices, like this. Okay? And so the two-colorability defect, what is it measuring? It's measuring how far is your hypergraph from a two-colorable hypergraph. It's the same as what we call a bipartite hypergraph. So I'm asking, how few edges must I delete so that my remaining hypergraph is two-colorable or bipartite? Okay? And that's the two-colorability defect. And what Dolnikov's theorem says, which is for any hypergraph, is that the chromatic number of the Kneser graph of that hypergraph is at least the two-colorability defect. Okay? Is the statement clear?
Yes.
It's a little much to take in, maybe. But there is a way to formulate this. So you take your hypergraph on these vertices here, okay? And now you want to color your vertices with 3 colors. Let's say I want to color my graph with yellow, green, and blue, such that any edge that does not contain a yellow vertex contains both a blue and a yellow. Blue and a green. And then I want to ask, the colorability defect is the fewest number of yellow vertices that you can do this with. Okay? So the yellow vertices are the ones I'm going to delete. So remaining edges should contain, the remaining edges are the ones that don't contain any yellow vertex, and they should contain both blue and green vertices. And the question is, how few yellow vertices can I do this with? Okay? That's the colorability defect. And the Kneser graph, well, the Kneser graph of a hypergraph, that's just the disjointness graph, right? So you associate each element, each set in your hypergraph, each edge, to a vertex, and you make an edge when they're disjoint. So this is more general than Kneser's conjecture, because it's dealing with an arbitrary hypergraph, and it's saying that the chromatic number of that Kneser graph is always at least the colorability defect. But you do get Kneser's conjecture. How? Well, consider the case when F is the set n choose k, right? Where n is at least 2k minus 1. Now I want to prove that the colorability defect is strictly greater than n minus 2k plus 1. Right? If that is true, then I get Kneser's conjecture. Then I prove the lower bound on the chromatic number of that Kneser graph. But if you delete a set of n minus 2k plus 1 from this vertex set, okay? From this set of points, So I have n points. I delete this many. I have 2k minus 1 vertices left. And I look at, and the induced hypergraph, so this guy here, after I deleted those vertices, is the set of k element subsets of 2k minus 1. This is not bipartite. Why is that? Well, you use two colors to color those 2k minus 1 remaining vertices. Well, one of the colors uses more than at least k colors. But there's a k tuple there. So it's not bipartite.
Oh, yes.
Right?
Yes.
So, in fact, Dolnikov's theorem implies Knese's conjecture, but it's more general because it's for arbitrary hypergraphs.
Is there a remember that this inequality is strict, or is it?
I don't know it, but probably. I wouldn't be surprised if that can be. So his question is there cases, can you make a hypergraph where you have a strict inequality here? And my guess is probably that can be found. I don't know what it is off the top of my head, but probably. To be honest, I don't think this two-colorability defect is a parameter that has been studied a lot. I think it was just introduced to give this generalization of the Kneser conjecture. Okay, so let's prove Dolnikov's theorem. One of your exercises is about Dolnikov's theorem. Actually, that's maybe the hardest exercise in this last set. So we need a lemma, and this is a very nice geometric lemma, which I like a lot. So did we talk about convex sets? Yes, we did define convex sets first class, but you know what that is. A convex set is a set that contains, for any 2 points, contains a segment between them. Okay? Now suppose you have D families, and each of these CIs is a finite family of compact convex sets. Okay? So, for example, here is a family of convex sets. Wait. But I suppose that each of the CIs is in fact an intersecting family. Okay, so here, so it means, as usual, they pairwise intersect, like this. So this is C1. Okay. Then I have another family. That wasn't intersecting, so let's delete that maybe here. C2. Okay. And you have D such families in RD. Then there exists a hyperplane that intersects all the sets. Okay. There is a hyperplane somewhere. In this case, a line that intersects every set. Okay. And this is, so what Dolnikov does is he pushes the topology into this nice geometric statement. Okay. Okay, so here is how we prove it. Take a direction, so I'm in RD, and I look at here SD minus 1. So the unit sphere in RD. Okay. And for a given direction x, I look at the line that it spans. Okay, so it will span some directed line like this. And I'll call that Lx. Okay. And what I do now is every convex set. So this is a convex set. If you take the orthogonal projection onto this line, you're going to get a segment like this. Right? And since if I look at all the guys from one family, this guy becomes another segment like this. It turns out all of those segments from a single family, they're going to intersect. because they pairwise intersect. So this is actually maybe needs a proof, but it's very simple, so I'll leave it to you. If you have a bunch of segments on the line that pairwise intersect, then they all intersect. Okay? So there's some common intersection, and there I define the point mx. Okay? So mx is the midpoint of the common intersection of all, I called it mix, sorry. mix, which is the midpoint of the segments that you got from family I. Yep?
The definition that MI is a midpoint.
You could maybe do it in some other way, but I prefer that it's the midpoint. You could maybe take the right endpoint or the left endpoint or something like this. But the main idea now is I'm going to start changing x. And then this point is going to move around. If you just took an arbitrary point and then for another x you took an arbitrary point, that point might not move continuously. So that's why I'm taking the midpoint, is I want it to move continuously. Okay? But I think probably if you took the endpoint of this interval, it should probably also move continuously. Okay? So anyway, that's a good question, but you need to choose the point in such a way that when I start moving x around, this point starts moving continuously. Okay, and this is similar to a proof we did yesterday. So now I'm going to define this function here, f of xi, or let's say fix, is x dot product mix. Okay, so basically I'm just measuring the directed distance to that midpoint. And the key observation here is if I were to choose this point minus x instead, right? So if I just switch the direction to the opposite direction, what happens? Well, the line, the undirected line is the same, but the direction now, L minus x, is pointing in the opposite way. What is the midpoint? Well, it's the same, except the sign of this guy, the sign of this guy changed. So that's an antipodal function, right? When you take minus, you get minus the same value. So maybe that's why I chose the midpoint, because if I said, say, the right endpoint, then what is the right endpoint when you're going in that direction? Well, it jumped over here, right? So maybe it's safest to choose the midpoint. But I think there are ways to work around this. Okay, and then you just, so then you define finally a function f from s, this is going from sd minus 1 to rd, which collects x goes to this f1x f dx. But wait, this dimension doesn't add up, right? That's not enough to use Bourse-Coulomb theorem. This dimension is one less than this. It's no good. But sometimes that happens, and then you need to go into your problem and see what are you really looking for. So instead, we define a function g, goes from sd minus 1 to rd minus 1, where x goes to, let's see, f1 of x minus fd of x, fd minus 1 x minus fd of x. Okay? So I'm just measuring the difference to this fd. Now this again is an antipodal function. Okay? Now it's an antipodal function from sd minus 1 to rd minus 1. So what does Bourse-Coulomb tell us? Say again? There's a 0, right? This function has a 0. So there is some x where this equals 0, which means this one is equal to fd, this one is equal to fd, meaning they're all equal. Right? So f1 of x equals f dx. And what does that mean? Well, it means all the midpoints were the same. Right? So m1 was equal to m2 was equal to md, which means this hyperplane, the orthogonal complement to this vector, at that point must intersect all the convex sets. Do you agree?
Yes.
Yeah. So that proves this geometric lemma. Okay, so now, we want to prove Dolnikov's theorem that the chromatic number is at least a 2 colorability defect. Maybe I'll write this down here. So this is our theorem. And we have our lemma. C1 up to CD. These are intersecting families of convex sets. Then there exists hyperplane intersecting every set in the union, C1, like this. Okay, so now let's suppose I have a decoloring of this Kneser graph. Okay? So it means I can partition the sets in F into F1 up to Fd, where they are intersecting families. Okay? That's precisely what it means that there is a decoloring when you translate it over to the set system. Okay, now the ground set. So this F is a family of subsets of some finite set X. Now I'm going to just take those elements of X and think of them as points in general position in Rd. Okay. General position here means let's see, I'm in Rd. So it means no d plus 1 of them are in a hyperplane. Okay. So for example, when d is 2, it means no 3 are on a line, etc. Now I'm going to define the following families of convex sets. So remember, the coloring gave me a partition of the set system. Okay? Now look at one of these, Fi, and look at all the sets that are there. Now you just take the convex hull. Okay? So from family 1, I look at all the sets there. I take the convex hull. It gives me a bunch of convex sets. Right? And I do this for each family. Now, clearly, each Ci is an intersecting family. Why is that?
Because if two sets have an element in common, then two of its convex hood also have a common
Right,
element.
right. So, I mean, if this was a triple that forms a set in F1, then, and here's another, here's maybe a 4 tuple, so. So not only do the convex sets intersect, they actually have vertices in common, right? Yeah. But that's not important. Each CI is an intersecting family. This we know for sure. Now, what does Dolnikov's theorem say? So now I have D, I was in RD, I have D families. Dolnikov's lemma says that, well, there's a hyperplane that intersects all the convex sets. Right? So there is this hyperplane, intersects all the convex sets. Now there will be some vertices that are here, some vertices that are here, and maybe some vertices that are here, right? That hyperplane could pass through some vertices, I don't know. But I do know, so this is H intersects C1 union CD. But I do know a bound on how many points are on that hyperplane. How many are there? At most D, right? So the number of points here, oops, is at most D. Okay, now let's look at, so the remaining sets or remaining convex sets, where are they living? Well, the remaining convex sets, if I delete these points, what are the remaining convex sets? Well, they have vertices from here or vertices from here. But actually, that's not quite precise. Not only do they have vertices from here or here, the remaining convex sets have vertices from here and here. There cannot be any convex set whose vertices only live on one side. Why is that? Well, this hyperplane isn't intersecting it, right? So all the remaining convex sets kind of pick up vertices from both sides. So I just color these vertices above with one color, green. I color the vertices that are below by blue. But the convex sets that are remaining here, what are they? Well, these are precisely the edges of the induced subhypergraph after I delete these guys. Right? So remember, I'm looking for the two colorability defect, meaning I want to delete as few vertices as possible such that the remaining induced subhypergraph is bipartite. But all the remaining edges, well, they must cross this hyperplane, so they must pick up vertices from this side and from this side, which means every remaining edge, after I delete these yellow points, is two-colored. So it's precisely what's left over is a bipartite hypergraph. And that's the proof, right? So we started with a coloring of the Kneser graph with D colors. And we showed, well, then the colorability defect is at most D. And so that's Dolnikov's theorem. And I think this is a very nice generalization of the Kneser conjecture. Now, one of the exercises, and I think this, in my opinion, the most difficult. Okay, so this is just the rest of what's going on there. The most difficult exercise in today's exercise set is to give a combinatorial proof of this in the case, let me see. Yeah, so the question is, prove Dolnikov's theorem for hypergraphs F with chromatic number of the Kneser graph of F is at most 2. So I think when the chromatic number is 1, I think it's pretty easy. What does it mean that the chromatic number of the hypergraph is 1?
There's no answer.
Hmm? Say again.
Independent.
Yes, it means an independent set, but what does it mean about, but we need to translate, so Dolnikov's theorem is saying, say you know something about, well, we're saying, suppose this is 1.
Intersecting family.
Yeah, what do I know about the colorability defect, right? So if you put the chromatic number is 1, I know that it's an intersecting family. So proving this or solving this question combinatorially for chromatic number 1 says prove that intersecting families have colorability defect 1. I think that's not too hard, but the difficult one is when it's equal to 2. It's more difficult. And for 3, I don't even know how to do that combinatorially, right? But that shows how these kind of theorems, although they're purely combinatorial, they are very complicated to solve combinatorially. And so that's what that exercise is about, to show that already for chromatic number 2, this starts getting very complicated. Okay, I'm going to quickly go through this last part I'm going to skip all this, skip the proofs, and just tell you the main result, which is called Shriver's theorem. So that's another generalization of the Kneser theorem. Okay, so remember, in Kneser's conjecture, we're dealing with this set of the ground set of our hypergraph is this set here. And then we're looking at the k-element subsets of there. Now, what Shriver discovered is he found a subgraph of the Kneser graph which has the same chromatic number. Okay? Now, what you do is you take the numbers 1 to n and you put them on a circle like this. Okay? So just put a circular order on those vertices. And we're going to say that a subset is stable if it does not contain consecutive points. Okay? So this is a stable set. Stable set. This is not stable. Okay? And the Shriver graph, SG and K, this is a subgraph of the Kneser graph where you only take the stable sets. Okay? So you take the stable sets and you look at the disjoint or the Kneser graph of the stable sets. So that is clearly a subgraph because you're only selecting some vertices, right? You're not taking all n choose k, you're only taking the stable ones. So, for example, when we took KG52, we got the Peterson graph. So KG52 was the Peterson graph, so that's a pentagon, 5 cycle like this, and was this graph, right? But if you take SG52, you get a much simpler graph. You just get the 5 cycle. Okay? That's just the 5 cycle. Now we showed already that the chromatic number of this is 3. But why was the chromatic number 3, not 2? Well, it was because there was a 5 cycle, an odd cycle, right? And what's Shriver's theorem, well, the Shriver graph 5,2, well, that is precisely just the 5 cycle, right? Has the same chromatic number as the Kneser graph. And so in some sense, you can think of the Shriver graphs as being kind of minimal graphs living inside the Kneser graph that force the chromatic number to be high. Okay? They are the ones that are really making the chromatic number what it is. So there's SG52. And the theorem is that for all n greater or equal to 2k, okay, you need to go up to 2k, that's not a problem. You have that the Shriver graph has same chromatic number as the Kneser graph. Okay? And yeah, we'll skip the proof. You can read it yourselves if you're interested. Right? It uses this moment curve. So remember last time we defined the moment curve, and it's based on some argument about the moment curve, some observation about the moment curve. So that's it. And I think let's round off here so we can start on the exercise set.